Okay, so yesterday we talked about bond polarity. Actually, we didn't really talk about it. We just reviewed it. We've done bond polarity before. It was in Chem 1. It was a Chem 1 topic. But what's different about bond polarity, you've just read in that little article, a little paper. It's actually from a text. And basically, this basically shows you, talks about how you do the vsepr theory. So if you read this article, it will tell you how to do that. Those of you who are absent can get this when you get back. But you guys just read it. And I tried to explain to you, hopefully, how you're going to do this. Okay? It turns out that it's very important, not just what the polarity of each bond is, but what the overall shape of the molecule is. You have to realize we're talking about a three-dimensional structure now, not just something in 2D. All right? Not just something drawn on a piece of paper. And I'm going to have to learn how to draw these differently, and we'll worry about that in a couple of chapters. We'll do a lot more drawings. For now, we're going to use models. All right? And I will... we'll be doing tomorrow, or maybe even second period, we'll even start this. I'm not sure how much time we'll have. We'll be starting a model lab. All right, we'll be trying. I have sets for you guys to play with. All right, but let's talk about what makes polarity different when you're talking about molecular versus bond polarity. All right, this is in your notes. You have this part, right? All right, you just read that little handout. Okay, molecular polarity. Well, this describes separation of charge across an entire molecule, not just across a single bond. Turns out, one bond can be pulling, one atom's pulling harder than another atom in a bond. But overall, there may be no charge across the molecule for a very good reason that you'll see. So it depends not just on what bonds you have and whether they're polar or non-polar, but on the shape or the geometry of the molecule. Okay? Now, turns out there are really two possibilities. If I want you to remember now. Remember what polarity is. Let's look at a model. Okay? Let's just say this guy's a chlorine atom, and this guy's a hydrogen atom. All right? If I look at electronegativity of chlorine like I did yesterday, I think that may be one of my examples, and I look up electronegativity of hydrogen, and I find that their difference is greater than 0.4, but less than 1.7. It tells me this. Chlorine is pulling, he has a stronger attraction for electrons. Those electrons are spending more time around his nucleus than they are around hydrogens. So this side of the molecule is going to be a little bit negative, and this side is going to be a little positive because electrons are negatively charged. Okay? So that's the basic concept. If I had two hydrogens, they're both pulling equally, there's no charge. Okay, this guy's pulling exactly the same as this guy. It's like a tug of war. All right, in a tug of war, identical clones of each. If I cloned Bailey, don't ask me why. But if I cloned Bailey, why anybody want to clone Bailey? But if I did, if she were pulling in a tug of war against herself, all right, that's what this is. Nobody's moving that rope. This is more like in a polarity, where you have a polar bond. This is more like two people of unequal strength. This is a weakling and this is a strong person. This guy's not so strong he can rip the rope right out of the other guy's hands. That would be an ionic bond. But he's strong enough to pull it closer to him. Okay. Well, if I have only nonpolar bonds, I have no choice. The compound has to be nonpolar. You can write that down underneath that, number one. Oh, it already is written down, right? Okay. No. All right. So if the compound has only nonpolar bonds, you know what that tells me? Nonpolar. No poles. No charge. Nobody's pulling any harder than anybody else. Doesn't matter how it's shaped. It could be any kind of shape. You can have 100, 1,000 atoms in that molecule. Makes no difference. If they're all nonpolar, the compound's nonpolar. Very, very simple. Problem comes when you've got polar bonds. There are two possibilities. Okay? You have that written down as well, too, right? Okay. First possibility. If you've got polar bonds and they are arranged equally and symmetrically, you are going to actually have a nonpolar molecule. Let me explain that. Probably the best example of this is carbon dioxide, which I hinted at just the other day. Okay, when we talked about carbon monoxide and carbon dioxide and its properties, remember I did a whole thing on carbon monoxide. Very short because properties, I talked about shape of every molecule, and I talked about how it's made and what it's used for. But then I did the same thing with carbon dioxide. I spent a lot more time on it because carbon dioxide is kind of more important. We did the fermentation lab, started that, all the different ways we produce it. We spent a couple of days on global warming and climate change. All right, we did a lot more on carbon dioxide than carbon monoxide. But in both cases, if you look back, this is the weird part. If you look back, carbon monoxide looks like this. CO. Carbon dioxide is CO2. But if you were to look back at your notes, you don't have to, you would find that this guy says it is a polar molecule. All right? And this guy says he is a non-polar. If you can spell non-polar. That doesn't make any sense until you look at the shape of the molecule. Look up, see, I told you to have your electronegativity sheets in front of you. Look up the difference between C and O right now. Hurry up. C and O. What's the difference between carbon and oxygen? So that makes them what? Polar. Everybody agree it's polar? So this makes sense. That one makes complete sense. This does not. Let me show you why this makes sense. Here, as you read in your vsepr theory handout, I hope, here is the shape of the carbon dioxide molecule, right here. Who's the guy who's got the higher electronegativity? The oxygens are the red. Carbon's going to be black. Oxygen's red. Who's got the higher electronegativity, oxygen or carbon? Oxygen. So which way is this oxygen pulling his electrons? That way. Which way is this oxygen pulling his electrons? That way. What do they end up doing? Besides breaking. What do they end up doing? Yeah, they cancel themselves out. It's like this guy's pulling this way and that guy's pulling that way equally. If I have equal, symmetrical, you know, I can draw a line down the middle, same thing on both sides. If I have equally arranged symmetrical bonds, I've got, even though this bond is technically polar and that bond is technically polar, the molecule itself is not polar. You understand? Now, you say, well, that's easy. I'm done. That's good. Well, it's not so easy. There's a couple of things that make this hard. Number one, they're not all going to be that obvious about the symmetrical shape. You're going to have to figure out what these shapes are. And that's why the back of that paper had all those different shapes on. You're not responsible for every one. You don't have to worry about octahedral and all these crazy shapes. You're going to have to know several. And I'm going to do as an example on the board. And it's going to take me at least the rest of this period and into the next. I'm not sure how much time we'll have. I think what we'll probably do is do a lab tomorrow. Even if we have extra time, I'll let you work on getting parts of this done. This is the lab for tomorrow. And then all you'll have to do tomorrow is build the actual models and check your work. So I know I'll get this done in the time I have. But that's what's going to get difficult about it. Two things. One is, what is that shape? And two is, just finishing the electron dot notations and predicting what that shape would be. That's going to be the tough part. And that's where the vsepr theory comes in. So predicting the shape, and then once I know the shape, is it really symmetrical? Because they're not all going to be as easy as this. All right, so let's take a look. Oh, by the way, that's for A. The other possibility is, for B, that I have non-symmetrical or non-equal polar bonds. Okay? In that case, the molecule's still polar. Now, as the case is for much of chemistry, that's, how many times did I say this in Chem 1? Well, that's all notes we have for today. We're going to spend 2 days talking about it, actually doing labs and doing examples with it. Very typical. Same thing, and by the way, what's atypical about, up until Thanksgiving for this organic stuff we're going to do, is there's really no math involved with it. That doesn't mean there's no problems involved. There's still problems. It's just not math problems, as you're going to see with my examples I'm going to do right now. All right? So let's do some of these examples. Y'all have the copy? All right? Okay. You have the same chart down below. I need you to kind of write relatively small, but I know some of you write bigger. Unfortunately, again, next year I think I'm going to remember. It seems like I was saving paper, so I made them both double-sided. But I think that's a mistake, because a lot of times what happens, like people who write bigger, they have to go onto the backside and do some stuff, and I probably shouldn't have done that. There is no backside to this, or is there? Oh, good. Well, then you do have time. Then you have room. Okay, good. Those of you who are right big, if you do write a little larger, because you are going to end up running into each other on some of these, and you don't want the electron dots to overlap. You may have to use the back. Okay, but we'll see how many. Because I'm going to do 1, 2, 3, 4, 5, 6 examples, and I don't think you can fit 6 examples unless you write really small. So let's do this. Dang. All right. Let's start with a guy like, if I told you you had HBr. Okay? You all have your common ions, your electronegativity sheets in front of you. First thing I want to look up is the electronegativity difference between these two guys and tell me what kind of a bond this is. Look up the difference between them and what kind of bond do I have. What's the difference between them, first of all? 0.62? All right, so if it's 0.62, that makes him what? Polar, non-polar ion? Polar. All right, so you write that. Squeeze that in small. Do not write this large. Keep that over there because you're going to need most of your room for the electron dots and the rest of the stuff. Actually, most of the room for the electron dot notation. Now I'm going to kind of...
Or bond polarity.
Oh, I have them in different orders? Oh, yeah. Okay, I'll have to change that for the other class. So
it's between shape and...
Okay, well... either way, you know what? Put this under bond polarity, even though your bond polarity column is a little further over. Leave the most room for electron dot. Let me refresh your memory on how to do electron dot notation. They're really not that hard. Okay? What do you do for electron dots? Well, I always told you last year to draw them separately first and see how many electrons they have in their outer shell. That's the most important thing.
And I got sodium instead of barium. Can I switch it?
Sure. And I got it right here. I was just using that last period. Yes.
Thank you.
That is the barium, right? I gave you the right one? Okay. So I always draw an electron dot first for each individual guy. So I have to draw H and Br separately. So I'll draw the H, and how many dots will he have around him? What group is he in? Yeah, even if he wasn't in group 1, how many electrons does hydrogen have, period? 1. Okay, so he has 1 dot around. I'm going to add to him the bromine, right? Bromine has how many dots around him? Br, he has 7. 1, 2, 3, 4, 5, 6, 7. Everybody agree? Now, I think I start with this real easy one because this is certainly this would not give us any trouble in Chem 1. The Octet Rule tells me everybody wants to have a filled outer shell. And for bromine, that's an obvious answer. That's why it's called the Octet Rule. How many more does bromine need? 1. Hydrogen, it's a little weird. Hydrogen is not exactly the same as everybody else because, look where hydrogen is on the periodic table. He doesn't want 8. How many does he want? 2. Okay. So how many does hydrogen want? He wants total now. How many does he need? No, total now. How many does he need? How many does he need?
6.
How many does he need? 1. 1. 6, 2, 7, 1. He needs 1. Where do you get 6 from? I have no idea. But anyway, a total has to be 2. So he needs 1 more. How many more does bromine need? He needs 1 more, right? You all agree with that? Okay. So they share. And they share unequally because bromine is stronger, higher electronegativity. And so what I get is HBr. It looks like that, right? We all would have written that, I would hope. Agreed? And I even had you all, though I don't really, you can still do it. I think it's probably not a bad idea. Write in your, an arrow, who's pulling harder, and which side be more negative, which side be more positive. And if I did that, and I used red here, bromine's pulling harder. This side's a little bit positive, the other guy's a little bit negative. Okay. Now, here's the deal. After you draw the electron dot, you're going to have to do these. That's why I said you're going to have time in the second half of this period to start these, I'm sure, because I only have 6 examples to do it. I won't finish them in this period, but I'll definitely get them done halfway through or less the next period. As you do each of these, you then have to predict the shape. And this guy, again, I start off with a nice, easy one, all right, because this guy, I can just use this one. This guy is very simple. Here's your H. Okay, there's your H. There's your Br. I use brown for Br. brown, VR, brown. Okay. And there he is together. What shape is that?
A line.
A line. Linear. 2 points in space can only be connected by a line, right? That's it. So this is linear. I don't want to use that. So we start off with a nice, easy one. Now, some of you might say to yourself, okay, well, what's the next question? Next question is this symmetrical? Is this symmetrical? Can I draw a line down the middle and have the same things on both sides? No. No. Some of you say, but a minute ago, this guy was linear, and I could draw a line down. Yeah, because I had an O on that side, an O on that side, pulling that way. Here, I got a bromine on one side, I got an H on the other side. One guy's pulling harder than the other. This side's slightly positive, this side's slightly negative. This molecule has polar bonds, and he is a polar molecule. Okay? The only way that would change is if I had symmetrically arranged polar. If I had another bromine, for example, over here pulling that way. You see what I'm saying? That would make it symmetrical. Right? Okay. All right. So there you go. That's a nice, easy one. We'll start off with a simple one. Let's do another one a little bit harder. Probably do 2 more of these before the bell rings, and then we'll get to the more difficult ones. This next one is a little bit weird. Okay, I'm going to have you do BF3. BFF. You're my BFF. You're my best friend forever, forever. That's BF3. Or it's boron trichloride. Either way.
The best part about watching these videos is hearing all your students.
Yeah, again. Because if you don't laugh the first time, I have to say it again. BF3. Now, again, I'll draw them separately. Oh, before I do that, look up BF3. What do you get there? Oh, I'm sorry, it shouldn't be BF. My fault, my fault. It should be BCl3. Sorry. All right. Because if you look up BF, you know what you're going to find? It's actually going to be ionic. So I want to use BCl. Sorry. So BCl3, my fault. Look up B and Cl. What's the difference between the two? 0.98? So that makes him polar again. Okay. Now, let me just say something here, people. If I had a guy, if I were to look up the first guy I look up here, the bond polarity, and he turns out to be nonpolar, I can skip ahead. If this guy's nonpolar, and the only kind of bond is nonpolar, what must this guy be? Nonpolar. If nobody's pooling at all, then there can't be a charge, period. All right, but this guy's polar, so I got to work it out. By the way, I want you to work them all out anyway. I want you to write electron dot notations for everybody anyway. All right, how do I do boron? Well, boron is going to be kind of weird. All right, there he is right there. Boron is kind of an exception to the rules. He only has 3 electrons in his outer shell, and he's not going to get, how many more would he need? 5, right? Not going to get 5 more from chlorine, because chlorine looks like this. And I need 3 chlorines. Okay, it looks like that. So the best he can do is to share one of these electrons with each of those 3 chlorines. Okay, to make chlorine at least happy, right? He's going to get his octet and share them. So I would draw that. I mean, there's a couple of different ways. I put the chlorines different places around it, but I'll put, obviously, who has to go in the middle? The B, right. So I'll put the B in the middle, and I'll put a chlorine over here, a chlorine over here, and I'll put a chlorine down here. I could have put the chlorine up top as well. Okay, it doesn't really matter, but I don't want to run him into the other guys. All right, now you'll notice, again, there's a couple of rules you got to follow when you do electron dot notations.
Good morning, everyone. Please pardon this interruption. We would just like to take this time to remind everyone that tomorrow morning, WBRE will be here to kick off our fall sports season. We certainly hope everyone is able to attend. However, we want to remind all students with junior driver's licenses that you are not permitted to be driving on the road until 5 a.m. Please be safe and adhere to this policy.
Interesting.
Thank you.
I love his voice.
I expect everyone to get up like 3 hours earlier.
No. He does, but no one else does. I don't think everybody's getting here. How many are? I guess the cheerleaders have to come. Band has to come, right?
Yeah.
Yeah. But, I mean, good luck. Have fun. I'll be sleeping. I'll think about you. I'll be dreaming about you. That's creepy. when you're parading. All right, look here. You watching? All right. So watch this. This is kind of interesting. This is where the first place we're going to use the vsepr theory. Turns out you got to use the vsepr theory to predict the shape of the molecule and its polarity. All right, you got to use that when you have more than just two atoms, because two atoms are always going to just be a line. I got to be able to predict. Here's what the vsepr theory basically says: all of these guys around the central atom are going to be basically negatively charged. They're either going to be a bond of electrons that are negatively charged and an atom with electrons around that are negative, or they're going to be a pair of unshared electrons. They're not going to be actually shared with some other atom, but they're still negatively charged. So I asked myself a question at this point, and this will be the last one I'll probably do because we've done for 2 minutes. I asked myself a question: how many things are bound around the central atom? And what's the answer to that? 3. All right. There are 3 things. Here's one of them. Here's 2 of them, and here's the third one. Everybody see that? Then the vsepr theory says, well, they want to get as far away as they can. How far apart can 3 things get? Well, let me show you. The furthest apart they can get, and I only have, this is the only guy I have that does this, is this. Okay? All right? This is the shape. And if you look on your back of your paper, what is the name of that shape? Yeah, and by the way, I've noticed that just looking recently, it's called triangular planar there, or trigonal planar, it might say in other places, okay? Triangular or trigonal planar. That's as far apart as 3 things can get. You see it? All right, so that's the shape. And notice I told you to say it's a lot of room for this here, but that's well, I want to use green. Trigonal or triangular planar. Triangular planar. They're all in the same plane, and they're as far apart as they could possibly get. Now, you guys have all had physics in here, correct? Pretty much, right? Do you remember physics with vectors? Remember vectors? All right, Mr. Schrader probably hung like a weight like this from the ceiling a couple of times, where it was supported by 2 different places, right? It had a weight holding them. Turns out that the downward force vector was equal to the vertical component, right, of these 2 guys added up, right? Remember that? Remember doing that? Okay. And that's how it would be no matter how I held this guy. This is a symmetrical model. It doesn't look as symmetrical perhaps as this obviously does, but it is. This is symmetrical because as hard as this guy's pulling, these guys are pulling the equivalent of that hard around him, okay? They're equal bonds, all arranged symmetrically. Now, what does that make this molecule? Non-polar. Non-polar. Okay? All right. Now, bell's going to ring in about 1 minute. So let me pause it here, and we'll come back and do the